Every mission in our fleet is really playing its part in the Artemis missions. Science enables exploration, exploration enables science. And we are excited about all of the missions that we have up there. These are going to really give us cutting edge, the newest measurements. We've been measuring space weather for a long time, but these are just going to be this next generation. And then, of course, a little bit later this year, we'll be launching Escapade, which will go and study basically the weather and the space weather at Mars. And so we really, really are playing our part in the Artemis mission.
And so with astronauts going back to the moon, how will that benefit us here on Earth, Casey?
Yeah, so, Artemis is more than just exploration, right? It's about inspiration. It's about national pride, national leadership. It's about economic growth. For every dollar that's spent at NASA contributes to multiple dollars in economic output. It's about technology advancement, AI, robotics, advanced manufacturing, and that leadership that NASA does, contributes across the world. And so that's really what Artemis is going to bring back to everyone here on Earth when we go.
Thank you so much for joining me, and I'm so glad that we could all be here for launch today.
It was a beautiful launch.
Yes, and thank you for having us.
Go IMAP.
Go IMAP.
Go Brothers. Go SWIFO.
Go NASA.
Thank you, Falcon.
Okay, so back to you, Megan and Kelly.
Go, 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 go. That's right, guys. All right, we invited you to send in your questions about today's launch. So Kelly is ready for a few more, yeah?
Definitely, yeah. Love the curiosity. Keep them coming.
Yeah, really great questions so far. This one's from Zayshan Ahmed. How long does it take to build and to integrate the satellites onto the rocket?
Yeah, these all took a long time. Satellites, 2017 was when this was initially proposed. And so then we took that time to actually build it up. Then you go through a design phase, then a build, then you actually have to test it once you've built everything, and then you're integrated into the spacecraft. So it's taken the time from 2017 to now. So that's around 8 years.
Yeah, and that's IMAP specifically. And then in that process, we identified the rideshare SWIFO L1 and Carruthers, yeah?
Right, definitely, yeah. So within that, then Carruthers was a little bit shorter of a time frame in terms of 21. It was approximately the time when it was turned on and started actually building. But before that, folks have been designing these and thinking about them for quite a while. We always have that next question in mind, and that next generation, always innovating here. So it takes a little while to get those innovations into print and metal and then launched on a beautiful launch like today.
Yeah, that's what's so impressive about scientists, always thinking about the next challenge and how they can meet it. So, okay, well, again, thank you for sending us those questions. Just keep them coming using the hashtag AskNASA across our social media platforms. All right, so the IMAP spacecraft was built by Johns Hopkins Applied Physics Laboratory in Maryland. Here with us now is Dr. Martina Goulidou, a project scientist with APL. It is so great to have you here, Martina.
So happy to be here. I think my heart is still racing.
I know. How was it to see launch today?
Oh, it was amazing. I teared up a little bit.
No, I'm glad. Again, this is so important to you guys. Again, she's part of the IMAP team.
Yes.
So really, we've been talking about the science behind what we're trying to study here with these spacecraft, describing the heliosphere as a bubble, right?
Yes, exactly. You can think of the heliosphere as a bubble that is being inflated by the solar wind, a constant stream of charged particles that is being emitted by the sun. Mm-hmm. So maybe we can pretend this little guy is our sun.
Yes, so Martina had homework for me. She asked me to bring some props. So I have a balloon and I have a balloon pump. So you're saying the pump is going to be like the
sun. And the solar wind. So the stronger the solar wind, the more the heliosphere is being inflated. Mm-hmm. And now when the solar wind gets weak, our heliosphere is being deflated.
Okay, so the pressure inside affects the shape, the size.
Exactly.
Yeah, so what about the outside, though? What is that expanding into?
Yeah, so the whole heliosphere is actually flying through our galaxy and what we call our interstellar medium, gas and dust that is existing between the stars. When the pressure from that medium is strong, the heliosphere contracts even more.
Even more, okay.
And when the pressure of that medium is weak, it allows the heliosphere to breathe again and expand.
So
there we
like
go.
This. Yeah. So basically, we are taking into account internal and exterior forces that changes the shape of the heliosphere. But why is that important to know?
Yes, so our heliosphere is actually a shield that protects us from harsh galactic radiation. So we don't know whether life would exist at Earth the way it is now if we didn't have that protective bubble, right? So it is important as we go and explore other exoplanets in other astrospheres, we want to understand first our home in the galaxy and how we came about.
And that's what IMAP's going to help us study.
Exactly. Go IMAP.
Oh, that's right. Go IMAP. Thank you so much, Martina. I appreciate
Thank
you
you
being
very
here.
much for
And
having me.
congratulations.
Thank you.
Congratulations. Okay, so IMAP is going to start collecting data about 3.5 months after launch. For more on that, let's bring back Joy, who's now with Dave McComas, IMAP's principal investigator from Princeton.